Today we will continue orbits, laws of planetary motion, and so we are shifting a little bit. Well, as time progressed, the discoveries that made got little advanced. We started to know more and more, and science is something that we build upon the previous discovery, previous invention. Kepler's discovery, Kepler's 3 laws were very helpful in determining the planets' orbits, planets' velocity as they go around the sun, planets' position in the orbit, and time period. How long does it take for any planet to go around the sun? Near the star, faster their velocity, so shorter the time period. Farther away from the sun, slower the velocity, hence longer the time period. And the shape of the orbit, the semi-major axis, the eccentricity, the size of the orbit, the semi-major axis, the inclination of the orbit with respect to the solar ecliptic. All this information we could extract from Kepler's and Brahe's and Copernicus and all the previous work. And on top of that, there was a more pressing question that was left for future astronomers, future scientists, and Newton took over. And that pressing question was, what is causing all these moons, planets to go in the orbit, circular orbit or elliptical orbit? And that's when Newton took over. And so in this section we'll cover Newton's great synthesis of laws of motion, including universal law of gravitation. And so these are the learning objective for this section. And here you can also see a almost complete animation of the solar system. Sun at the center, all the planets orbiting around it. Farther out planets are slower compared to the nearest, Mercury. And now we also know there is a huge belt, a large belt with tens of thousands of rocks, we call asteroids, between Mars and Jupiter. Every now and then they collide with each other and they change the orbit and they come towards Earth. It has happened in the past. When those asteroids come in, they bring in a lot of energy, 10,000 times stronger than a nuclear bomb, the energy equivalent. And they have wiped out civilizations, they have wiped out, I shouldn't say civilization, they have wiped out animals and plants of the earth few times, and that can happen in the future. And so this is a picture of our solar system now, and then let's look at the Newton's contribution. Isaac Newton, born in the year Galileo died, January 4, 1643. He was a miracle premature baby. They thought he wouldn't survive without intensive care like we have these days. Premature babies rarely survived in the past. They lived through the plague. Everything was shut down in England due to plague. All the scientists, students were ordered to stay home, but Newton defied all that. He stayed in the lab. Actually, he stayed in the lab all his life. Never dated, never married, just doing science, and a lot of science and math. His contribution is in calculus, developing laws of motion, developing universal gravitation law. He also worked on optics, making these glasses, explaining the polarization, diffraction, interference properties of light. What else? Oh, he also worked on the chemistry. He was working on with some chemicals, doing experiments. He played a lot with mercury. He inhaled mercury vapors, and he died in his sleep, sadly. That's his life. So again, during that time, he worked on laws of motion. Oh, I have a song for you, a rap battle. Let's get back to physics, Newton's laws. I will not get into more mathematical details. On the surface, very conceptual. We're trying to, based on the laws of motion, we'll build to our higher order thinking to explain the universal law of gravitation. And so Newton, in his time, he published this. I think this is the most popular book ever written in science. Philosophy Naturalis. The natural philosophy was the name of science in the 1500s. Instead of science, they call it natural philosophy. The name science was coined much later. Principia Mathematica, or in short, just Principia, published in 1687. He didn't want to publish. He was not a guy to publish or make money and go for fame and name such type. He had all written everything in the corner left over, and his colleagues, rich colleagues, kind of assisted him in all that publication part. And so in that, he explains these three laws. First one, called Newton's first law, law of motion, which states that every object continues to be in either a state of rest or a state of motion, unless it is acted upon by an external force. For example, this stapler here is going to be in its state of rest all our life, all forever, right? Unless it is acted upon by external force, meaning unless I provide some force, or there is gravity to shake the whole building, and so on. And same thing with motion. If we push something, and if this is a completely frictionless surface and there is no air friction, and I apply some force to it, it's going to slide. It is stopped because the external force like friction was acting on it, and it is stopped. But if there was no friction, then it would continue in its path forever. And that's what happens in space. There is no air friction. Some of these objects, satellites, if you give initial force to it in space and leave it, it's just going to drift forever. And that was the first law. And he did get help from Galileo, who had previously, hypothesized or put some words or explained what that all is, the first law is. He didn't call it first law, Galileo's first law. He wrote in terms of the momentum. Momentum is the measure of a body's motion. Mathematically, momentum is mass times velocity, mass of an object times velocity. Any moving object has certain velocity. At rest, velocity is 0, so there is no momentum. But any object in motion, they have velocity and they have mass, so that's the momentum. And Galileo had put that the momentum of a body can change under the action of an outside influence. If there was no external force acting on it, the momentum would not change. Newton simply rephrased it. So I should give an example. Good example, when you are driving at 60 miles, 50 miles per hour and you suddenly slam on the brake, your lower body that is attached to the car, because car is stopping, your lower body on the seat, stops, but your upper body is loose, not connected, and so your upper body, continues to move in motion. If you don't have seat belts, that's when the people just get fly off, break the windshield as well. Again, because the body is in state of motion, the car is in a state of motion, your body, the passenger body in the car is in a state of motion, but when you suddenly apply brakes to the car stops. But the person inside continues to be in that motion, so it moves forward, and it's same thing with the cyclist here. Second law states that when I apply force to any object, like this one here again, I'm applying some force. It's at zero velocity, zero acceleration. When I start to apply force to it, it accelerates. The acceleration is directly proportional to the force applied. Higher the force, higher the acceleration. And it is inversely proportional to the mass of the body. If the mass is higher, for the same amount of force, the acceleration is less. For example, the guy applying force to a cart with some mass, it accelerates. More force, more acceleration. But if I increase the mass here for the same amount of force, for higher mass, the acceleration decreases. And mathematically, we can combine these two statements as F equals ma, or force is equal to mass times acceleration, one of the most popular equations in physics. That's Newton's second law. And third law is action and reaction. Every action has equal but opposite reaction. When I push something, it pushes back. Pull out your thumb and at the edge of the desk, press it. You are pressing, you're applying force against the table. I say edge. Now if you look at it, you see a dent in your finger. Not just that you were applying force, the table was applying the force, the reaction force against your thumb, and hence you see the dent. Okay. And other examples, that's how the rocket flies. The force on the hot gas, downward action, the reaction, it applies the downward force of the gas has equal but opposite reaction, opposite force. Equal, same force, if it's 10 Newton downward, it's 10 Newton upward, but opposite, hence the rocket flies up. That was Newton's third law. Okay. And more physical quantities, more definitions. These are, we are used to with it every day. But let's formally define it. What is mass? Mass of an object. It's the measure of the material, measure of the particles that are inside of an object, within an object, the measure of the amount of material, unit. Again, we measure in pounds, kilograms. What else? Even gram is the unit. But here I say unit kilogram because that's the standard international unit for mass in kilograms. And the next is volume. How much space does that object occupy? That's the volume. Its unit is cubic meters. Meter cubed. Density is the measure of compactness of a system, how compact an object is. Definition is mass per unit volume. So you divide a mass of an object by its volume, you get the density. Compactness explains everything about density because this stapler is much denser than a piece of wood. So the materials in it, the particles in it are in this stapler are much more compact. The density of iron is more than the density of a wood. And again, we're dividing mass by volume. And the angular momentum, another physical quantity. I introduced it during the last lecture when we try to explain the area subtend, during some time t, same time t and t in any orbit, that area would be same. So now let's look at more in terms of angular momentum. So it's the measure of the rotation of a body as it revolves around any central body. The formula, angular momentum is mass times velocity times radius. An object, so call that moon, that's Earth. That moon goes around the Earth in that orbit. It has some linear velocity in that direction. Its radius is distance. Center is, we always measure the distance from body center to the center. Like Earth and moon, when we say R, it's the distance from center of the Earth to center of the moon, not the surface distance. And so that's R, and M is the mass of the moon. So we say the angular momentum. L is, it's the notation for angular momentum, just like mass is M, volume is V, density is Greek letter rho, angular momentum is L, capital letter L. And so the angular momentum for the moon would be mass times distance, R times its velocity. And so there is always conservation of angular momentum when objects go in this type of circular or elliptical path. The conservation of angular momentum means whatever the angular momentum an object has when it is at this point, what's the angular momentum here? mvr, mass times velocity times this distance, r, from sun to the planet. So I can find a product, MVR, let's say that MVR comes out to be 100. And so whenever the object is here, its product or its the angular momentum magnitude must also be 100. The momentum is conserved between going from here to here. But what's the formula? Mass times velocity times radius equals 100. But when the object is here, is this radius same as that? No, the radius has gone down. If radius is decreased, but the product should be 100, the mass is constant, the mass is not going to change, so what must change? The velocity. So velocity goes up, hence the velocity of the object at the periapsis, pericenter, we call the nearest distance from the sun, that orbital position is pericenter. We'll come to that later in dynamics. But that's pericenter. At pericenter, the velocity is higher compared to the apocenter or aposis because of the conservation of angular momentum. Meaning the angular momentum at A, the product of MVR, must be equal to product of MVR at B. If one quantity goes down, the other quantity must go up. So these two quantities are equal anytime in the orbit. Okay, that was the conservation of angular momentum. It's a Olympic season, Winter Olympics. See, there's a skate, figure skating. They display conservation of angular momentum in a very nice way. You have seen when their arms are spread apart, even their legs are spread apart, and when they rotate, they have certain angular momentum. And next thing, when they bring their arms closer together and legs closer together, now all that mass that was spread out in longer or bigger radius, all they are now is closer to the rotation axis. But if the product of my MVR or my initial angular momentum was 100, it has to be 100 in this position, but now the R has decreased. The velocity must go up, so the spin rate is higher. When they have to spin faster, they give some force. When their arms are wide apart, they start rotating, and when you bring their arms closer together, they spin even faster. Applying conservation of angular momentum to win a gold medal. And now the actual universal law that Newton was able to devise based on his observation of the things around. The first law, what does it state? Every object continues to be in a state of rest or motion unless acted upon by external force, and usually things move in a straight line, that as we observe on Earth, and if you give some push to any object, it moves in a straight line. And so the common thought was that maybe straight line is a more universal form of motion. And everything we observed around were traveling in a straight line, would travel in a straight line. When things fall, they fall down in a straight line. But all the observations made by Kepler, Tycho, Copernicus, and himself, showed that the objects, the planets, moons, they were traveling in ellipse. So what was causing them to bend in their path? It says object continues to be in a state of motion in a straight line unless it is acted upon by an external force. So all the planets were moving in a straight line, but an external force is causing them to change that path. What is that path? That's what ignited Newton to think and to invent gravity. And he said there must be some force. The moon here is moving in a straight line, but there's a force between Earth and moon, the gravitational force between two objects. And that force is directed radially towards each other. And that force of gravity here, force on 2 due to 1, this force is directed radially towards the center of the Earth. and it has some velocity v linear at that point. So I'm being pulled that way because my velocity is in that direction, linear velocity. I'm also being pulled by the Earth's gravity that way. So now I take the middle path. I go diagonal one step. And next step, same thing. I have a tangential motion, radial motion this way. So I end up going in a circle every time, because every time I have a linear velocity, linear speed, and the central force that's pulling me towards the centripetal force and the linear force. And hence every object go in a circular path towards their central body, or moon go around the Earth. All the planets are being affected by the gravitational force of the sun, and bigger the mass, bigger that gravitational force. And so our sun's gravity extends quite far out, and its gravity is influencing all the planets and satellites and orbits, satellites in orbit, to go around the sun. And that, I think that was the biggest observation, biggest scientific discovery by Newton. He also hypothesized that gravity is not limited to Earth, and this is a general force attraction between all objects in the universe. And there's a gravitational force between this pointer and this stapler. So if anything has mass, naturally there is a gravitational force between these objects, and that's an attractive force. Gravity is an attractive force. We know something about magnets. Magnets, if they're opposite poles, it's an attractive force, but if the same poles of a magnet are a repulsive force. Gravity is always attractive. And there is an electric force. Electric force can be attractive and repulsive. If you same charge, same electricity charge, negative and negative is a repulsive force, creates repulsive force. If I have two positive charges, they create a repulsive force. Positive charge and negative charge create an attractive force. They attract and move towards each other. But the gravitational force between any two masses is always attractive. And there's a gravitational force that exists between two galaxies. The clusters, we call the group of galaxies together, two clusters of galaxies, they attract with each other. There's that force of attraction between me and the desk, and me and all of you. And so it exists between every material in the universe. That's why it's called the universal law of gravitation. And one equation, this equation here, can be applied to any object in the universe to find the gravitational force between two galaxies, two moons, two dust particles, and between the stapler and the pointer. Same equation can be used. That's why it's called the universal law. And again, there are two more hypotheses that he said. What does that force, gravitational force, depend on? The mass. So the masses. The force is directly proportional to the product of the masses. Bigger the masses, bigger is the gravitational force between those two objects. Smaller the mass, smaller the force. You can calculate the gravitational force between these two objects. 1 meter apart, 1 kilogram, half kilogram. 1 meter distance, gravity, this gravity, this constant of gravity, universal gravitational constant is 6.67 times 10 power minus 11. That's a constant number. So you can use G number here. M1 is 1 kilogram, half kilogram, distance is R. Calculate F, force due to gravity between these two objects. You'll get a very small number, very, very small number. But if you use same equation to calculate the force of gravity between the sun and the earth, because the mass of the sun and mass of the earth is much, much bigger, we get this force of gravity much higher. And so, this gravity field extends around the earth. So there is gravity field right now, and when there is mass, like this one here, it's being pulled, always pulled towards the center of the earth. And so that's why it falls. The gravity is, this attractive force. That's why it falls. Right now, we are being pulled towards the center of Earth, and it accelerates. When it falls, it accelerates with certain value. That acceleration, or we call it the acceleration due to gravity, 9.8 meters per second squared, we always accelerate downward with G. And so there is a difference between mass and weight. Mass is just the measure of physical quantity in this stapler. That is mass. But it's weight. When I say weight, it's mass times gravity, mg. It's giving me force. You remember previous equation, force equal to mass times acceleration? Acceleration is 9.8 meters per second squared, always downward. And its mass, let's say if it's 5 kilogram, so its weight is 5 times 9.8 close to 10, so 5 times 10, about 50 Newton. And his finding, his discovery of gravity, G value, had enormous consequence in our space research. All these satellites that we have today, all the rockets we launched, are contribution of his findings. Okay, let's find out how in orbit and mostly the satellite motion to follow. And so now we understand the force of attraction between two objects in the universe. Sun is the big guy, the major player in the solar system. Its mass. So all the mass of the solar system, including the sun, sun has 99.9% of the mass, and forget how big Jupiter is, all the mass on the Earth, all 9 planets, dwarf planets, asteroid belt, all that mass is less than 0.1%. So sun is that big. The sun's gravity field extends so far out, and it's been able to have all these planets and moons and asteroids in orbit around it because of the controlling gravitational force that it has. And there is a bigger picture. All these black lines are planets, The blue lines are asteroids. Here. And these, the blue are asteroids. Black lines are planets. As you see, the planets look very circular in their orbit because their eccentricity is close to zero. Here you can see the eccentricity of all the planets. Closer to zero, more circular they look. If that number increases, goes towards 1, their orbit looks very eccentric. For example, some of these satellites and comets, they have much, the blue ones here, their satellite, their orbit is quite eccentric, so they look flattened, their orbit. And these comets here, these comets, they have even more elliptical path, elliptical orbit, because their eccentricity is so high. Among, you see here, the Mercury has the highest eccentricity, but the second one is 0.009 for the Mars. And that helped Tycho Brahe, to hypothesize that the orbits are in elliptical path, and since Mars displayed the most elliptical path, if it was closer to circular like 0.01, his observation he would not be able to definitely tell the orbits are ellipse. He would just assume they are circular. But because Mars had that's a lucky coincidence. Because Mars had the highest orbit or highest eccentricity, that helped him. And here are some facts. Again, Mercury, closer to the Sun, has higher orbital speed, 48 kilometers per second, or 88 Earth days to go around. Earth days. Neptune, the farthest one, is 165 years to go around. 250 some years for the Pluto to go around. You go farther out, the velocity decreases. Kepler's law. And the inclination-wise, compared to ecliptic, the plane, they are not in exact same plane. The orbits are, some orbits are a little higher to a reference line. 17 degrees for the Pluto, 7 degrees to Mercury. The Mercury orbit is 7 degrees inclined with respect to a plane. Earth is close to zero, so it's on the same ecliptic plane most of the time. What else? Next is the finding of Newton. He extended his thought experiment because there was no way he could fire a rocket engine and test it at that time. So these are his actual diagram. He had a thought experiment. He's standing on the top of a hill. When you throw something, I have a chalk. I'm going to throw chalk around. It's I'm giving it a linear velocity in a straight line. Okay? So it moves in a straight line when it leaves my hand, but as soon as it leaves, it's going downward. It has some speed. It has a force in a straight line, also the gravitational force from the earth pulling it down, so it moves in a curved path. Okay, let me increase the speed. Okay, it went farther out. Let me even shoot it with a higher speed. It goes farther out. If I can have enough power, if I can apply enough force to it, I can, shoot it to point A. With higher force, shoot it to point B. If I can give enough speed, do I have a number here? Somewhere, 8 kilometers per second. If I can shoot it at 8 kilometers per second, you see, it tends to go in a straight line outward. At the same time, the gravity is pulling it down, and so it goes straight, but gravity pulling it down, it goes farther out, farther out. It's falling every time, but since it has this linear speed higher, it never reaches the Earth. So it's constantly falling. So any satellite, all these astronauts in space, they are not floating. We shoot them with certain speed, and now they are constantly falling around the Earth, but they never reach the Earth's surface because they have a linear speed enough to keep them in that falling orbit. And that was a thought experiment until Russia, back then it was called Soviet Union, they launched Sputnik, first artificial satellite with that speed. And they saw it orbit around the Earth. And that changed everything. All our telecommunications, all our communications that we have, our GPS satellites, our weather satellites, all came from this finding. Firing a bullet, a thought experiment from Newton, now a reality. And so everything that's out there, they are falling into Earth's, trying to fall into Earth's surface because it's balanced by their linear speed and the gravity. They constantly fall. What's the speed? A lot. 17,000 miles per hour. It's that, with that speed they are falling. If everything was floating, then there would not be, have you watched the movie Gravity, Sandra Bullock? You know, because things are falling, and you know, if two objects falling with that speed come in the same line or in opposite direction, that's going to break the whole space station. And another interesting fact, why does this rocket burn when they come back to Earth? The re-entry, like why does there is so fiery ball every time? The friction, right? If it was, it's not, we know it's not floating. It's traveling at 17,000 miles per hour, and there is not much air to cause that friction. And now when they have to enter the Earth's atmosphere, any object with that speed hitting the atmosphere, that's what causes that fiery ball. These are the pieces that surround the Earth. It looks nasty, and it is not dangerous, too dangerous in a sense. These are smaller objects, and if it is small enough, when they enter the Earth's atmosphere, they disintegrate, they burn out. Unless they are huge asteroids, they don't burn out, and they reach the Earth's atmosphere and bring all that energy to destroy, can destroy Earth or civilization. There are satellites, thousands of them, all, you know, many developed countries in the world. There's a competition, you know, if you want to put your own satellite, your own defense satellite, your communication satellite, your radio satellite, TV satellites, and now Elon Musk is putting thousands of internet satellites.
Space too.
And yeah, there was a car too, right? There's a car orbiting in the solar system, and there is a timing of about 90 minutes. Again, it depends on where in orbit, different height, closer to the Earth, faster. and you go farther out from the Earth, that is speed slows down, so time increases. Some low Earth orbits are not indefinitely stable. When they hit the Earth, they are closer to the Earth's atmosphere, and sometimes the Earth's atmosphere changes in density. When it hits up more, it expands out, and it may reach where the low Earth orbit satellites are, and then those satellites start to burn, they disintegrate, and they fall. Most of them, they don't reach the Earth's surface, like I said. They're burned completely within the atmosphere. Sometimes they do reach the Earth, bigger parts of the space station, and they plan it so that it falls in either in the Pacific or Atlantic, nowhere near civilization. You can calculate that trajectory and make it fall exactly where you want.